All right, so I think it's already like time, so we should start. So today's speaker is Samson Leung. He's a grad student at Carnegie Mellon University, and he's gonna talk about axiomatizing AECs and applications. Thank you, Samson, for agreeing to give the talk.
Yeah, thank you, Marcus, for giving me the opportunity to present my paper, which is the same title here, Axiomatizing AECs and Applications. So my research is more to the pure side of model theory. I know there are a lot of people working in algebra here. So one thing that I can ask everybody is to come up with like examples to see whether the results that I present today are optimal or not. And I would suspect that they're not far from optimal, especially in algebra. There should be a lot of properties that allow the theorems to improve. So the overview of my talk is that I will present the statements of the main results. So I'll give you what I proved in my papers. And then I will describe the axioms of AECs. Since Marcus has already described the axioms briefly last week, so I'll go through that quickly. And then I'll go through the proof idea of one of the theorems. If there's still time, I'll go through other results and talk about open questions. If you have any questions, just stop me when I'm talking. So before I state the main result, I would like to give some definitions to the notations. So let's say you have two first-order languages, L and L prime. T is a theory in the bigger language, and gamma is a set of types in the bigger language. And I say a model is in ECT gamma if the model satisfies T, but omits gamma. If you take the redux of that model to the smaller language, then I say the smaller model is in PCT gamma L. So it's a known fact that Scherer proved the presentation theorem. The statement is that let K be an AEC, and lambda is the Lowenheim-Skolem number. So this is a cardinal associated to an AEC. Then he proves that the class of models in K is PC lambda 2 to the lambda. So let me explain what the two parameters lambda and 2 to the lambda mean. It says that the first cardinal lambda is the size of a theory T, and 2 to the lambda is the size of gamma, which is the set of types. And I can write down K as a PC class with that theory T, that set of types gamma, and then you take the redux to the language of the AEC itself. So in an AEC, there's an associated language. So what we do is we first consider a bigger language. We satisfy some theory T or with some types gamma, and then we take the redux to the original language. So Scherer proved this result, and it's like the very beginning of AECs, and I always ask myself, can we improve this statement? Or can we make more assumptions to improve the bounds? And obviously, the first cardinal lambda seems natural because it's just LSK, which is associated with the AEC itself. But the second cardinal seems huge. It is 2 to the lambda. As long as you don't assume GCH, then we hope to see what are the cases when the second parameter 2 to the lambda can be lowered. So this is my motivation. How can we control this gamma? And my paper 4.1, my first result is that we can write down K actually as PC chi chi. The cardinal chi is lambda plus another parameter called I2 lambda K. So a quick fact is that this cardinal must be bigger than or equal to lambda. So we won't have any improvement in the first parameter. We might be worse in terms of the first parameter. But luckily, this cardinal is bounded about by 2 to the lambda. So as long as we know this cardinal chi is strictly less than 2 to the lambda, we can improve the second cardinal or the second parameter here. So in some sense, we're sacrificing the first parameter for the second one. And we will see like towards the end of the talk, I'll tell you some applications of why we care about having the same parameters here and why we are willing to sacrifice the first one for the second one. So that's the theorem statement. And here I don't make any assumptions, just like Scherler's original results. There's no assumption here, no other assumptions here. And you look at Scherler's result, it's hard to see if we assume, let's say, categoricity or stability, how the parameters can be improved. But if you use my result and the general proof strategy in my paper, then we can conclude the following. Let's say the class of models K is categorical in lambda plus. It is stable in lambda, has lambda amalgamation property, and there are at most lambda many models whose size is lambda. If you have all these assumptions, then it is PC lambda lambda. So there's a lot of assumptions here, and you can make like 5 to 6 different variations of this result, depending on what assumptions you want to make and how you want to replace them. And if you are familiar with model theory in abstract elementary classes, the key idea is that we want to build limit models inside this class so that we can have this improvement here. And you may ask, okay, are there any other results other than the Scherler's original one? Here's the following. So like many years later, Scheller and Vasey, he proved the following result. Assuming K is an AEC with Lower-Skolem number, which is countable. So here is a huge restriction that the result only applies to countable LSK. And now you can try to compare the result with my statement above. They're basically the same, but my result assume an extra condition, which is categoricity in lambda plus. And everything else, you can just substitute lambda equals to Aleph naught. And then they conclude that K is PC Aleph naught. So there are two comments that I can make here. The first one is that the results use discrete set theory. So that's why the result only applies to countable Lower-Skolem number. But my result assumes something more, which is categoricity in lambda plus, because I wanted to do something with limit models. So this is one of the main results in my paper. And let me go on to the next one. The next one is a variation to this theorem 4.1, 4.10. Here, if you look at 4.1, let's say, we're actually changing the language to a bigger one, omit some types, and then taking the readout. So there's some change in the language itself. My next results will keep the original language, but requires an infinite tree logic. So let's see the results by Scheller and Villabezes. They let K to be an AEC. Let's say L is the original language in the AEC, and lambda is LSK. They proved that you can axiomatize the AECs by a sentence in this logic with the same language. And here they have a huge conjunction complexity, but the quantifier complexity is lambda plus. And so obviously we want to see, can we lower this cardinal here, which is too complicated? And the second thing I want to see is, can we simplify the proof? So you look at the paper, they use some partition theorem in set theory, and they try to build a canonical tree of models and somehow to color them, and then they can use the partition theorem to get some results. So I myself am not familiar with those partition theorems. And since the general question of axiomatized AECs is quite general, and at least the question statement is simple, so I always ask myself, can we just find a simpler proof, maybe with the same complexity here, or maybe higher, or maybe lower? So what I've proven in my paper is that I cannot really just lower it to a smaller cardinal. I need to make also some sacrifices. Again, we have the same assumptions here. And then we have the same friend chi, which is lambda plus I2. This time I can axiommatize it by sentence in this logic. So let's forget about the brackets later on. As I mentioned before, chi is bounded above by 2 to the lambda. So my complexity in terms of conjunctions is lower than Schroeder and Beer's version. But the unfortunate thing is that I need to change the logic a little bit. I need to allow gain quantification with omega times omega many steps. So gain quantification simply means you allow infinite alternation of quantifiers, and the number of alternations is omega times omega. So there's some sacrifice. I have a lower complexity, but I have to assume some gain quantification in the logic. So that's one way to trade off. But the nice thing is that my proof is relatively simple. So as long as you understand the usual proof of Schroeder's presentation theorem or the papers by Barney and Vasey, then you understand my proof pretty easily. So I will talk about the proof, not 3.7, but the previous one, which is 4.1 here. I'll give some general proof ideas of how do we carry out this kind of proofs and what results will we use. Any questions before I move on? So if not, let me just go through some axioms of AECs, because if we don't know what we are like handling, then there's no hope to prove anything. So AECs are some axiomatic framework developed by Scheller to contain certain classes of models. So one key feature is that it's a generalization of first order theories. And you may have seen in Marcus' talk, there are a lot of other examples which are of interest in algebra. The definition is as follows. So let's say we have a first order language L. When I mention an AEC, I don't just mention the class of model, which is the light phase K here. I also have a partial order to the models. And for convenience, let's call the language associated with the AEC L. So I want to say this ordering respects the L substructure relation. So it respects the relation and function symbols. And next, it should respect isomorphism. So if one model is in K and the other is isomorphic to it, then the other one is also inside K. And you want to say the same for the K substructure relation here. So here's a diagram, but the idea is that if things are isomorphic, then they should be equal. And the next three axioms are less trivial. And my proof mainly uses number 4 and number 5, which are just axioms of AECs. Number 4 is coherence. Coherence says that if you have a triple and the first two is less than the third one, and the first one is a Leung substructure of the second one, then we can conclude that the first one is actually a K substructure of the second one. So remember, K substructure implies L substructure. So it's kind of an upgrade that you have this weaker condition, you want to upgrade to a stronger one. And the way you can conclude this result is that you assume they are dominated by a bigger model. Number 5 is the Lowenheim-Skolem axiom, which is basically downward Lowenheim-Skolem theorem in first order logic. There should be a cardinal lambda such that for any model and any subset in it, you are able to close it into a K substructure N, and the size is not bigger than the Lowenheim-Skolem number lambda plus the size of the subset. And in general, this cardinal might be much bigger than the size of the language. And number 6 is chain axioms, which basically means that the models in AECs, they are closed under chains, increasing chains. So these are the axioms of AECs. And if you want to know, okay, what axioms we actually care about in our proof, it will be number 4 and number 5. So some more definitions. So it is appeared in the statement in my theorems. I lambda k simply means the number of models of size lambda up to isomorphism. So here it's just individual models. We can do the same for pairs of models. I2 is simply the numbers of pairs of models, where let's say the first one is a k-substructure of the second one. Both are of the same size in lambda. And how do you identify two pairs of models? You first find an isomorphism between the bigger models, and the restrictions should be an isomorphism for the smaller models. And a simple counting argument will show you that I2 is bounded above by 2 to the lambda. So in my rank result, I mentioned the cardinal chi a few times, and let me record it. Chi is lambda plus I2. So you can see it's between lambda and 2 to the lambda. And one like naive approach when we try to improve this result is that, oh, we assume more properties of the AECs, and maybe we know better about I2. But it turns out it's not the case. When I try to improve the result with more assumptions, let's say categoricity, stability, and so on, I'm not trying to get a better control of this I2. I'm trying to use limit models and other machineries to tell that K is some smaller PC classes. So one question that I can give to everybody is that, are there some interesting examples in algebra, let's say, where you can compute I2 and it is slightly less than 2 to the lambda, assuming you don't have GCH? So now we know what are AECs and we know our theorem statements. So what we also want to know is what the machineries can we use besides going all the way from definitions. So the main tool or definition will be about directed systems. So let me define what is a directed system in an AEC. A directed system is a set or a class of models indexed by some I here. And the requirement is that whenever you have two models, let's say Mi and Mj, you can always dominate them by a bigger model, also in that system. So what kind of index set can we use? Well, in Schiller's original proof of his presentation theorem, and also in my proof, I'll just use the easiest system, which is index them by finite triples of elements in M. So let me draw something so I can slow down a little bit. So let's have an M indexed by a singleton A. And then I have another model M indexed by another element B. So right now I have just two models. If I want to make sure it's a directed system, then it's better for me to have a bigger common model indexed by MAB. So this MAB might not be the union of M and MB. It might be bigger, but it always exists if we have the Lowenham-Skolem axiom, close them under some common models. So if you have another MC, and you may want to do the same here. So A, B, C. But the idea is that we're just indexing the system by elements, like A, B, and C. And here we're doing inclusion. So the biggest model here are indexed by ABC. The ABC contains A and B and C. So it is a superstructure of the rest. So here is just a diagram. So you look at the axioms of AECs, and you can quickly prove by induction that a directed system, assuming all the models in the system are inside K, then the union is also inside K. The union is also the least upper bound of all the MIs. So when you have another model N containing all the small models MI, then N is bigger than the union. So it's just a fact about directed system. But it'll be useful because we don't always want to build chains. Chains are more difficult to build. Directed system are easier to do. Especially we can do finite tuples as an index set. So now we know that we need some directed system so we can take the union and become a model in K. We know the index set is just finite tuples of elements. So how can we write down a sentence or some theory to capture that? So let's simplify the situation a little bit. Let's say I just want to define a theory T such that the following happens. I want to prove M satisfies some theory T if and only if M is in K. So my job is to find this theory T here or some other axiomatization, and then we'll try to prove the by implication. Because my axiomatization is relatively simple, it's quite easy to do the right to left direction. So because I will just need to state something about coherence, Low-Hampstead axioms, and so on, they're almost like immediately implied by the axioms of AECs. So the interesting direction is always from so let's say we're doing the left to right direction, and we try to figure out what is T. So let's let M to be an LK structure. So it uses the same functions and relation symbols as any other models in the AECK. And then you have lambda as the Leung number. I know that if we have a directed system inside K, the union is in K. So why not just make sure that M is the union of some directed system? And all the MIs are inside K. So we can do that, it's good. So when you make sure that we can talk about small models MI, which is inside K, and we want to talk about those models are directed. So let's do the first one. Remember, we're talking about PC classes, so we're going to expand it to a bigger language first. The way I do it is the same as Schiller's presentation theorem. We add LSK many functions. So let's call them Fi here. And how do I define, or how the function symbols work? If you're given a finite tuple A, so let's say A is a singleton for convenience. And then we have lambda many functions. So if you take all the possible image of Fia, where I is changing, then you get a subset of size lambda. I want this subset to enumerate some K structure MA. So it's an enumeration here. And you don't need to worry about how they interpret the relation to function symbols, because in the assumption here, we assume M satisfies, let's say, some axiomatization T. Everything should follow the interpretation in M already. So all we need to do is just find the correct subset. So this part is not too difficult. Okay, just say, given an element or a tuple, I can close it to a model, and that model contains A. So how do I actually write down as an axiom or a sentence about this MA is in K, because we don't have set theory? we don't have this like set membership symbol. So the way I do it is that I first list all the possible models in K lambda. And you ask how many models are there in K lambda, it'll be I lambda K many. And to each model, you will need an infinitary logic to write down all possible relations and functions in that model. Just list everything out. So we can list all the possible models. And if you ask, okay, when is MA is in K, then you just say MA is in one of these many disjunctions of the isomorphism types. If it hit one of them, then it means it is a model in K of size lambda. So right now we have tackled the problem of ensuring the MI here. If you want to define a directed system, the MI is in K. The second thing we want to do is, how can we talk about directness? So I want two models, and then there's a bigger K superstructure. So this is what I wanted to do. If you have two posts, so here there might be more than length one. If A and B are subsequences of C, then I want to make sure that the MC that I enumerate dominates both MA and MB. So how do we do this? Well, we just do the same. We just list all the isomorphism types of this time pairs. So in some sense, I'm doing the proof by brute force. Just list all the possible pairs. And this time we have I too many. And whenever you have a pairs of models, satisfy one of the isomorphism types here, then they're isomorphic to N0 and N1 respectively. So once you understand, maybe let's say point one here, then point two is not surprising. You're just carrying out the same proof. And we find ways to get a better parameters. It turns out that I cannot just find a way to lower I2. It seems I2 in many cases would be just 2 to the lambda, which is kind of annoying. So what I will do is use some machineries called limit models and try to do some coding with the limit models. Oh, before I talk about the get around way with the limit models, so let me continue with this proof here. So we have axiomatized the individual models, and we also axiomatized the pairs of models here. Remember, we are still in the bigger language, in the bigger logic. So how can we guarantee that, okay, we need to take the readout of the language and so on? So here is the trick. Right now we're in a bigger logic. Let's say L prime is the language with extra function symbols for me to enumerate the small models. And chi is lambda plus I2. So technically it could be, you can write as lambda plus I1 plus I2, but I know I is less than I2 anyway, so I just write that I2 here. So right now we are in some inferential logic with some sentence. But I want to talk about PC class. So I use the following result by Chang. Chang's presentation theorem says that if you have a theory in this logic here, and you only care about a fragment of size less than or equal to theta, where theta is this cardinal here, then you can actually recode the class into a PC theta class. And the way Chang's presentation theorem works is they add a lot of relation symbols to represent the conjunctions and disjunctions. And let's see how we can use the theorem here. We simply take chi equals to theta, and everything else will work. because we're only having like a sentence, so we don't even need to worry about will the fragment get too big or not. So you take T is just a singleton set of sentence, which is sigma here, right? Then we know K is PC Chi class. So that's why I have the result at the beginning, 4.1. So now I can try to do some like quick improvements to my proof. So let me write down what I had at the beginning. If you don't have the rest of assumptions, just the straight up part, just ignore it for now. I could prove it is PC Chi. Now I want to add these bunch of assumptions here. I want to say K is PC lambda lambda. So let's see how we can prove that. We don't change the number one in the proof idea. So number one, I mean this part here. We don't change anything. We still do use the same proof. And the reason is that I assume I lambda is less than or equal to lambda. So if you want to know the complexity, let's say of the conjunctions, it is at most lambda. So this part is, we just carry through because by our assumptions in the statement here. So this is small, so we don't need to worry about anything. Now, what about the second part of the proof idea where we talk about the directedness of the small models? This time, I don't want to just say, okay, there's a bigger model that dominates the two small models. I want to have a special relationship between the bigger model and the smaller model. So let's fix a small model first. Let's say it's M0. Now, in the original proof, I just take M1 to be any K superstructure of M0 using the Leung axiom and coherence axiom. In this improvement, I require that M1 is a lambda omega limit model of M0. And you may ask, okay, what's special about these limit models and when can we obtain this kind of limit models? Basically, what I wrote about guarantees they exist. And what's nice about them is that if you have two versions of limit models over the same base M0, you can actually get an isomorphism from M1 to M2 here, fixing the base M0. So let's assume we have only one base in this world, and we try to consider what is I2. Well, we have M0, M1 as one pair, and M0, M2 as another pair. Because this isomorphism already fixes M0, it witnesses that you have only one pair in I2 up to isomorphism. But now in the general case, we might not have just one base. We might have like many different bases. So I need to use the assumption that I is less than or equal to lambda. So I can consider different small bases. So unfortunately, I've already used 0, 1, 2 here. So let's say I call the first small base M0, M1. And then let's say we have the last one called M lambda, let's say. Then I know that to each small base, there's only one way to create a limit model. So let's say N1 here. This is N0. And now you ask yourself, how many pairs up to isomorphism exist in I2? Well, with lambda many, because this is one pair, this is one pair, and so on. You have lambda in total. So here I really need to use the assumption that I lambda k is unabove by lambda. And to carry out the rest of the proof, originally I say if you have MA, MB, you can dominate by some bigger model MC. You just need to change the phrasing. You have MA and B. You want a common bigger model, which is a limit model over the original two models. And that uses stability amalgamation property. So that's it of the proof idea of my main result. And remember at the beginning, I mentioned I also have another axiomatization, keeping the same language, but using some game quantification. The proof idea is the same. There, I don't have new function symbols, so I cannot keep track of what subsets are K substructures. And I have to sacrifice to compensate this. I need to use game quantification, which is infinite alternation of quantifiers, to allow me to build a directed system within omega times omega many steps. So it seems is inevitable to me that you have to have some like foreign objects, let's say extra function symbols, or some strong enough logic, let's say game quantification, in order for the model or the K structure, the L structure, to recognize what is the K substructure of it. So let me draw something to state my remark here. So let's say I have a L structure, M might not be inside K or not. It seems there's no easy way to encode some substructure MA such that MA is a K substructure of M. So this is the hard part. You can easily say that MA is in K. So you just want to say MA is in K. This part is easy. The hard part is to say that MA is a K substructure of M. And if you have somehow a very easy way to encode it, then you already somehow imply M is in K, which is kind of the circular. So that's why it's not always easy to do this. All right. So here is the proof idea. Or instead of doing the same proof idea for the game quantification version of it, I want to state some applications mentioned in the abstract. So before I do that, I have like a huge definition here. So for those of you who are not familiar with the well-ordering cardinal delta, such that if of type at least delta, then you can find another model where the ordering is ill-founded. And the fine print is that they're all about EC classes, and the lambda k are about the parameters. So we won't need to do any proofs with this property. So here, just for you to take a look. And that's another definition I need to do is for each ACK, we can define an induced class, which is K less than. So what I'm doing is just list a pair of models. So it's basically like I2. But here I'm just considering as another class. So with these two definitions, I can state Shadow's original result. Remember, okay, I said at the beginning that I'm willing to sacrifice the first parameter in the PC property here. I'm willing to sacrifice the first one for a smaller second one. The reason is basically this theorem here. Shadow proves that if both K and K less than PC theta theta, so that's the first assumption. The second assumption is categoricity in both theta and theta plus. The third assumption is the crazy ordinal delta and apply to parameters theta and 1 if it is equal to theta plus. If you have these three assumptions, then you can predict the existence of models in theta plus plus. So notice that we're doing everything here in smaller cardinals, theta and theta plus, and then make some predictions in K theta plus plus. The proof is totally non-trivial because you have this technical cardinal here. But for our purpose, we just focus on the first and the second assumptions. So originally Scherer proved that any AECK is PC lambda 2 to the lambda. So this is Scherer's result, lambda 2 to the lambda, where lambda is LSK. And you may ask, okay, how can we satisfy the first assumption? Well, if you use Scherer's original result, then you have to take theta to be at least 2 to the lambda. So you have to take the maximum of these two parameters here, so they can fit to this format. If you use my result where I have PC chi, well, it's kind of trivial. You just take theta equals to chi. So I can say that my result can show that assumption 1 is true when theta is bigger than equal to chi, which is lambda plus I2. And then I have a bunch of assumptions to guarantee K is PC lambda. So one of them is like lambda AP, one of them is stability in lambda. And the other two assumptions happen to be here. So remember, one of the assumption is categoricity in lambda plus, which is here. The other assumption is there are only lambda many models of size lambda, which is actually the weaker condition stated here. So somehow like Scherer's theorem statement like does a favor for me, and I can just skip two of the assumptions and just say that if you assume this true, you can basically forget about this assumption and take theta equals to lambda. So which is like an improvement as long as you have small I2 or you are willing to assume more assumptions about the class. So let me clear this. Two more like results related to my paper. So what I've proven so far is the first row here. If you have an AECK, then I can tell that K is PC chi. And I can also encode it in terms of some gain quantification. Here, chi is lambda plus I2. Lambda is the Leung score number. It turns out that my proof can be basically copy and pasted to the mu AEC context. Mu AECs mean the same axioms for AECs, but you not allow the language to be infinitary. And you also allow the chain axioms to be weaker, where you only have a bigger model inside K when not just an increasing chain, but you require to be a mu-directed system. But because my theorem statements or my proofs work with directed system, so you can think of AEC is just the Aleph not directed system version. And here we have the mu-directed system version. So I can basically tweak some of the parameters and everything will work. So I can say that in terms of mu AECs, K is a PC chi with a superscript mu. Here it is to indicate that the languages are infinitary, so less than mu. And when I do the axiomatization, I can replace the number of steps by mu times mu. And the reason I need to do this kind of adjustment is that if I just have a directed system, it's not guaranteed that the bigger structure is inside K, or vice versa is not true. I want to have at least a mu-directed system. And in order to do that, I need to have a lot of steps, or I need to have a bigger logic to capture this. And what about this like chi here? It seems they're not changing. Well, chi is this cardinal here, which depends on lambda. Lambda is LSK. And if you look at the definition of LSK for mu AECs, this cardinal is sensitive to mu. So usually if you have a bigger mu, then lambda is also bigger. So it's like a swept under the rug with the notion of LSK. So I don't need to change anything. I just keep this chi and this lambda here. So one comment is that maybe because my proof is general enough to work for also mu AECs. So in terms of original normal like Aleph not AECs, there should be some room for improvements, because here my proof is so general. It can work for any mu AECs when mu is bigger than Aleph not. So maybe I'm not using enough properties of AECs themselves. Okay, finally, I want to raise some open questions. So previously I asked, okay, are there any interesting examples, maybe in algebra, where you have a small I2? Another way to ask the question is, using the extra assumptions I stated in my theorems, can I actually lower I2? Remember, I didn't do anything to I2. I simply talked about limit models to have a better result. So that's one open question. The other open question is, in the other version of my theorems, I use some game quantification, which is of this kind of format. So here just some dummy variables. Are there any interesting relationships between a usual infinitary logic with infinitary conjunctions and quantifications with those having game quantification? So obviously, if you have the same alpha beta here, then the right-hand side implies the left-hand side. If you can find some way to encode the game quantification one with the usual one, then that might remove the game quantification in our axiomatization. And finally, it is about like a pure model theory where we want to talk about half numbers. Half numbers is the threshold cardinals for arbitrary large models to exist. The format is as follows. So it's just a fact here. So the half number, you can compute it as beta sub delta lambda k, lambda kappa. So this delta lambda kappa is the technical cardinal I introduced a few slides ago. And what are these lambda and kappa? We use lambda and kappa when k is PC lambda kappa. So if you want to have a better understanding of the half number, then you want to know about this delta lambda kappa. But these lambda kappa are from the parameters in this PC class. So ultimately, if you can lower the complexity of this PC lambda kappa, you are able to compute the half numbers better. So that's for the AEC case. For mu AECs, we don't have the same proof because it's not we're not using a first order language. We're talking about infinitary relation symbols and function symbols. So a similar question can be raised for mu AECs. Can we find some proofs that show the half number exists, or more properly, can we compute it like the formula above? So the above is only for AECs. Okay, that's all I want to present today, and thank you for listening. If you have questions, please let me know.